Hi everybody, I'm Fabio Luporini. I'm one of the lead developers of Devito. And here I'm going to talk about what Devito is and how we implement the GPU support in our framework. I just want to spend a few words talking about what makes Devito so special, so different than legacy codes or traditional libraries. To say that you need to implement a particular form of the wave equation for your inversion code, what do? So assuming there's no existing library that exactly fits your needs, what you do? You pick up your favorite language, C or Fortran, and write an implementation for one specific equation, a set of equations for one particular discretization, and so on and so forth. And this can already be quite challenging. Now, at some point, you are going to need to focus on performance because these codes need to go fast. So you'll have to think about parallelism, optimizations for cache locality, GPUs, if you want to run on GPUs, and so on and so forth. So these can easily get extremely challenging. Now, in the real world, these can get even more challenging. It gets even more challenging because realistically, you're going to need not just an implementation for the forward propagation, for example, but you are going to need an adjoint as well. You may be interested in multiple forms of the wave equation. You may want to play with different discretizations. You may want to be able to run on CPUs as well as GPUs and so on and so forth. So the space of codes that a company or an academic group or people in general typically need to implement and maintain and extend is huge. So this is a challenging problem. So the question here is, can we do something to tackle this problem? And the answer is yes. That's exactly what we try to do with Devito. And at its core, we are not doing anything new. What we are doing is applying again the same trick that in computer science and mathematics as well has been applied over and over and over again, which is raising the level of abstraction. So instead of writing an implementation in C or Fortran, what do? Well, we use an intermediate language. So what you see here in this slide is the Devito DSL, the Devito domain-specific language. And as you can see, there's a clear relationship between the terms of the DSL and the mathematics. And then what do we need? Well, we need a compiler that takes the symbolic specification of your problem and generates the efficient code. And so this is Devito. So Devito is the language and the compiler to generate efficient code. Just a few more details to avoid any confusion. So Devito is a DSL and compiler for explicit finite differences, primarily. You can also use it to implement fairly arbitrary stencil codes, but that's a different story. So it's got an open source license. It's a Python package, though clearly the compiler generates low-level code, potentially with MPI and shared memory parallel. As of a few months, we also support GPUs, which I'm going to talk about next. And just one more comment, we take the software engineering pretty seriously with lots of testing, continuous integration, and so on and so forth, which is the key to robustness and therefore the key to for a wider adoption and to building a community around the project. So we are using Devito for seismic imaging primarily, but today there are open source projects in different areas, so including medical imaging, neural networks, CFD, finance. And now GPUs. So more generally, every time that you have, so like you have your own code written in C, for example, and at some point you want to port it on GPUs, there's a number of things that you have to think about. Now, if you're doing inversion, and Devito is a package designed to implement inversion codes, essentially, so you really need to think about a large number of things, not just the performance of the kernel, but also about the data movement, and in particular about the data streaming. So for example, the saving of the wave field every n iterations, the prefetching of the wave field when you are computing the adjoint of your equation, and so on and so forth. You also need to think about multi-GPU support. So you may want to be able to run on multiple GPUs concurrently via domain decomposition, or you may want to be able to run different shots of the same computation in parallel on different GPUs. So there's a number of things that we need to think about and need to be able to support. So this is already quite hard, but what really is hard, so much harder, is the automation. So Devito is a compiler, right? So for any sort of equation, for any sort of problem written with the symbolic language, it doesn't even have to be finite difference. So the compiler must be able to generate functional, efficient GPU as well as CPU code. So this is extremely challenging, as you can imagine. And so how do we tackle this complexity? So, and again, the answer is resorting to one of the key pillars of computer science. So we decompose a hard problem into easier sub-problems. Devito is a compiler. A compiler is compilers, like every compiler, essentially produce low-level code applying a series of transformations, so a series of compilation passes. And Devito does exactly the same. So we have a hard problem, which is the generation of GPU code. We decompose it into a number of tasks, into a number of compilation passes. And each of these compilation passes in isolation doesn't do much, but all together they achieve the purpose. So they achieve the goal. And this is the key to maintainability and extendability. Okay, so I'm just going to show you an example of how this works. So what we have here is the isotropic acoustic wave equation, and with this further equation here, we are expressing the fact that we want to save the wave field every, say, n time iteration. Okay, so that's the purpose of this equation. Now, the dots that you see here are placeholders for code that I'm going to show you next. So what do we do? So what does the Devito compiler do? So first of all, it analyzes the symbolic specification that the user has written. So the first thing that it realizes is that you say, like this object here, would be too large to fit in the GPU memory. So the compiler decides to keep usave on the CPU. And then what the first pass does is using buffering to decouple the CPU execution flow from the GPU execution flow. So the compiler introduces this equation, U buffer equals U. So U buffer lives on the GPU, okay? And so there's going to be a GPU, like there's going to be a thread driving the GPU computation, which computes the isotropic acoustic wave equation and at some point saves a slice of the wave field into this buffer. Another thread running asynchronously on the CPU takes copies the data from the GPU buffer into the corresponding CPU buffer and saves it on usave, which, as I said before, is an object, is a piece of memory which lives on the CPU. So that's what the first compiler pass does. And as you can see, this transformation occurs at a very high level at a very high level of abstraction. So I'm not showing any loops here. I'm not showing any abstract syntax trees yet. All I'm showing is symbolic equations. So we have two threads running concurrently, asynchronously. So clearly we need synchronization mechanisms. So we need a mechanism to wait on locks and to signal the CPU thread when there's new work that needs to be performed. So in particular, the copy of ubuffer from the GPU to the CPU. So the second compiler pass is in charge of analyzing equations, detecting the data dependencies, and placing the synchronizations. Third pass, we are further lowering the intermediate representation that we had before into something more concrete. So now we have an implementation for the weights for the synchronization mechanisms. And everything here is an abstract syntax tree. So we are progressively getting closer and closer to the code that we want to generate. And finally, we do what we call the specialization for the target language. So until the fourth pass, there's no trace of the language that we are going to use to generate the code that we are going to run. And it's only when we reach this pass that we decide that we start using a concrete language to implement specific actions. So in this case, I'm using OpenACC to perform a copyback of ubuffer from the GPU onto the CPU. So we have decoupled the lowering of the symbolics into low-level code through a series of 4 passes. If I want to generate CUDA code or OpenMP code, all I need to change is the 4th pass, not the previous ones, which are applied on a more abstract intermediate representation, but as I said, only the last one. And this is the key to extendability and maintainability. So this is one of the core, probably one of the most important takeaway messages of our GPU work. Well, not just the GPU work, but of the methodology that we use in Devito. So just a few words to conclude about the performance that we got. Like, this is an isotropic acoustic benchmark that we ran on an NVIDIA v100. Here are the details of the benchmark, and the key numbers to notice here is that are here. So the kernel runs at 27 gigapoints per second, which corresponds to about 53% of the attainable peak on the roofline. So this is an aggressively optimized version of the OpenACC implementation of isotropic acoustic. Register pressure is limiting the performance today, and it's part of future work to get around these current limitations. Just want to thank all of the sponsors who have supported Devito since the very beginning, and I'm concluding showing the GPU support roadmap.